I'm just adding another little coral story here that just came out in the proceedings of the National Academies of Sciences in the US. And basically, we are looking at another set of corals now in the eastern tropical Pacific, which gets hammered by El Niños every few years. And we know that the frequency, duration, and intensity of El Niños have changed over the Holocene and also during the last few centuries, as far as we can track with paleoproxies like corals themselves, sediments, and other things. The point is, when we talked previously about heat tolerant corals and symbiotic algae that help them survive, we talked about genetic traits which worked to pick heat tolerant corals. This is a cute study because it looks at El Nino timescales, which happen every few years and hammer the corals to create a bleaching. So if you look at the recovery of these corals, what is happening? That's the main story here. Let's read the abstract. Climate change is radically altering coral reef ecosystems, mainly through increasingly frequent and severe bleaching events. So as the temperatures warm, El Niños put warm temperatures on top of those, so the so-called degree heating weeks, the number of weeks over which accumulate heat above a certain threshold that is harmful to the corals, can be tracked. Yet some reefs have exhibited higher thermal tolerance after bleaching severely the first time. So what do they do once they get bleached? You would imagine that if they are living in a place that gets hit by El Niños frequently, then they must have somehow evolved to survive these regular perturbations, right? To understand changes in thermal tolerance in the eastern tropical Pacific, we compiled 4 decades of temperature, coral cover, coral bleaching, and mortality data, including 3 mass bleaching events during the 1982 to 83, 97-98, 2015-16 El Nino heat waves. Higher heat resistance in later bleaching events was detected in the dominant framework building genus Poecilopora, while the other coral taxa exhibited similar susceptibility across events. So Poecilopora seems to have learned from the first bleaching event to acquire heat-resistant symbiont algae, which then protect it from these heat wave events. Genetic analysis of Poecilopora SPP colonies and their algal symbionts during 2014 to 16 revealed that one of 2 Poecilopora lineages present in the region, so Poecilopora 1 type 1 and type 2, increased its association with thermotolerant algae symbionts, the Durusdenium glynni, during the 2015 to 16 heat stress event. This lineage experienced lower bleaching and mortality compared with Poecilopora type 3, sorry, not type 2, which did not acquire this glynni symbiont. Under projected thermal stress, ETP reefs may be able to preserve high coral cover through the 2060s or later, mainly composed of Poecilopora colonies that associated with Durusdenium glynni. However, although the low-density, high-cover reefs of the ETP could illustrate a potential functional state for some future reefs, this state may only be temporary unless global greenhouse gas emissions and resultant global warming are curtailed. So this is now a required caveat in almost everything we do, which hopefully doesn't affect our ability to see how biology adjusts to these chronic changes, so temperature changes, sea level rise, etc., and acute changes like hurricanes, heat waves, etc. So significance in their own words: global warming is causing the loss of coral reefs worldwide as a result of heat-induced coral bleaching and mortality. Here we examined the potential mechanisms that have increased the heat resistance of dominant framework building coral taxa Poecilopora on the reefs in the eastern tropical Pacific. We refer to this as ETP. We proposed that increasing abundance of a thermotolerant symbiotic alga, Durusdenium glynni, hosted by these corals, has facilitated the maintenance of high coral cover after 3 mass coral bleaching events. This study reveals a mechanism by which some reefs may be more resilient than previously thought, and illustrates how future reefs might still maintain high cover for several decades, albeit with low diversity, provided other stressors are minimized. So these are some data looking at 1982, 83, 97, 98, 2015, 16. There is the bleaching threshold in terms of degree heating weeks in degrees C per for a number of weeks, and there is the mortality. So here we are looking at the yellow dashed line marking the 4 degree heating week threshold for the 4 DHWs, 4 degree heating weeks. For likelihood of bleaching, and the red dashed line marks the 8 DHW threshold for likelihood of mortality. Red crosses denote the dates when colony assessments of bleaching and mortality were performed and the corresponding maximum heat stress levels experienced in the 6 months prior to the time of the survey. So here we are looking at the 3 events, the 3 big events, 2 biggest from the 20th century we had on record, and the first big one in the 21st century. And we are looking at the period here, January to October, and July to July here, and July to July here. And basically are looking at Procellopora cover percentage wise, going from the 1980 baseline to there are various numbers here of where the samples were taken and how large the plots were and the chain of transects, etc. But the main idea is that the first hit that these corals took, the ones that learned to acquire Durstinium glinii, did well after they got hit with the last of the El Niños. So they have developed a memory from the first hit they took to see how they can survive. So there is another symbiont alga that doesn't have such high heat tolerance and doesn't protect the corals as well. So if you look at total symbiont to host cell ratio SRH for the 2015-16 period for type 1 and type 3, you can see that the cladocopium is not the heat tolerant one and the Drusudinium is, and if the coral switches from the cladocopium to Drusudinium, then it acquires heat tolerance and does better in the next heat wave, whereas type 3, which didn't acquire it, basically had much smaller symbiont host to cell ratio sorry, symbiont to host cell ratio, which means it didn't acquire the tolerance. This is showing the same thing conceptually. So you're looking at Drusudinium dominated colonies in percentage and Procyllopora's cover in percentage, and you are looking at El Nino 1982-83, which had degree heating weeks of 7.6, and then there was a drop in estimated Drusudinium dominated colonies, and then the 97-98 El Nino hit with degree heating weeks of 10.3, and you can see that there was selective mortality. So that was the switch symbiont shuffling, where you went from cladocopium from Drusudinium. So then you did better in terms of recovering the percentage of Procyllopora cover here. Okay, so here again you are looking at the hit from 2014 to 2016 El Nino event that was a bit extended, 2015-16 being a big one. So you can again see there was selective mortality, symbiont shuffling, and then heat tolerance acquired. They used this idea to basically see with various future projections like SSP 5-8.5, SSP 5-8.5 with different higher bleaching thresholds acquired, let's say, by this adaptive capacity of the coral, then how long could they survive? I don't want to spend too much time on this because I think there is just way too much uncertainty in this, because we haven't really nailed down how El Niños respond to global warming in terms of duration, intensity, and frequency. We still haven't figured out if the East Pacific will continue to warm or warms more slowly or faster than the West Pacific, because that determines the east-west resistivity gradient and the feedback and how much heat the ocean will continue to take up, and so on. So there are uncertainties here, but nonetheless the optimistic message is that with this adaptive capacity in response to bleaching events, the eastern tropical Pacific corals could presumably survive out to 2060 or so. But again, the caveat is that biodiversity will go down, colony coverage may go down, density of the corals may go down, and we have no choice but to reduce, decarbonize, go to net zero, and so on and so forth. But it's a cute enough story that I just wanted to include a short podcast here, continuing the previous discussions on nature's rules and biological loopholes, where we looked at species of birds after wildfire, polar bears surviving without sea ice, and corals genetically predisposed to selecting Ducidinium glynni for surviving warming, and so on. Okay, this is a nice story basically because it's looking at very fast time scales, El Nino time scale response. So if there is genetic adaptive ability to quickly learn from bleaching events, then we have some good news, right? So that's what I wanted to conclude with.